We're really pleased to have Professor Joseph J. Williams here today. He is an assistant professor at the University of Toronto in the Department of Computer Science. Prior to that, he was actually an assistant professor at National University of Singapore, and he actually has a rich history. Before that, he was a research fellow at Harvard studying advances in learning, and also did a postdoc at Stanford University subsequent to completing his PhD at Berkeley. So he's been at all sorts of places, which really speaks to the strength of his research and work, and as comprehensive as his history and where he's worked is his publication record. He's publishing in all the top journals and articles in HCI. He's doing a lot of work in how we can improve education through technology. And what really excites me most about Joseph's work is, as HCI designers and researchers, we're always trying to iterate on our designs and improve them and give the best possible thing we can to the users. What if we could release designs into the world that actually improve themselves automatically? And Joseph's doing some fantastic research exploring new ways to do this that can lead to a new paradigm, really, of how we think about technology evolving over time. That it's not just up to us to improve it, but using different strategies, which he'll talk about, they can improve themselves. So really exciting work. Let's give a hand to Joseph.
Thank you. I like how Toby summed up my research. I feel like he summed it up in a more inspiring way than I do sometimes. I'm going to try and, I think I'm recording this, yeah. So just letting you guys know I'm recording this. Who knows if we have a look at it, but it's easy to record. So one thing I'll start off by saying is that I'm originally from the Caribbean, from Trinidad and Tobago. And I have to tell you now, because people say that they miss the first part of my talk trying to guess where this strange accent is from. So now you know I'm from Trinidad, the mystery is solved, and I have your full attention for all the scientific content, right? So another thing, I would just do some kind of quick, announcements in a way. I'm really excited to be here in Toronto. I did my undergrad here, but coming here is like being in a totally new world. So I'm very new to HCI and user experience. So if any of you have suggestions for companies or people who want to do consulting or industry work like in A/B testing, I'm really interested in thinking about applied problems. Like Toby said, how can I consult or work with companies who want to actually deploy technology that keeps improving itself through A/B testing? Or if you have any tips for events I should be attending or people I should talk to, I welcome them. The way I kind of run things for my group meeting, so the group I'm in I created is called the Intelligent Adaptive Interventions Group, and you'll see why that is. But we actually run our group meetings online, so we allow people to come and give guest talks. You can listen by Google Hangouts, we can record them and keep Google Doc notes. So if you're interested in it, feel free to send an email to that address, ieiinterest@googlegroups.com. If you just want to be added to a mailing list or present. And we probably also have some people present remotely. A lot of my collaborators across the US and Canada. I'm teaching a grad course this semester, which is all about machine learning for A/B testing. And so I have the resources, I'm adding them slowly. So that's one website, but if you're interested in getting those reading lists or materials, feel free to contact me. And I think, I guess I can jump into it from there. So the kind of focus of this talk is going to be, one more announcement. So now that I'm in computer science at U of T, a lot of my research is in education. So if you know people who want to apply for PhDs where they're actually doing research on learning education in a computer science department, well, now U of T will take those people. So if you have any friends who are interested in that, please feel free to tell them to apply this year. We're trying to get it listed that you can actually do computer science education research at U of T. As you'll see, I do a lot of research in health as well. So I'm also open to other domains, especially as long as they involve A/B testing and machine learning. All right, so in terms of what I'll talk about today, and let me switch into slow mode because then people can actually follow me. So what I'm really excited about is, like Toby said, how do we kind of deploy a user interface into the world? An online course, an app, and then keep improving it. And so my approach is to reimagine A/B experimentation as the engine for that. So how do we design A/B experiments? By using machine learning to figure out what works for different people, and also human computation. My approach to AI is that you actually need algorithms interacting with people. So how do we actually involve people in crowdsourcing the designs of A/B tests? And I'm going to give you a lot of examples from education, but while I present, I hope you can just keep thinking in the back of your mind, where would I use this? When would I want to collaborate on design A/B tests? Whether it's in health, whether it's in improving your website, whether it's in marketing. So in terms of thinking about intelligent A/B testing for enhancing personalizing, here's some examples, and you can think of your own. One is in education or learning. What if we want to A/B test which explanations help different people to learn? Another might be apps for mental and physical health. How do you help people learn how to change their behavior? For example, you might want to A/B test which messages do we give someone to motivate them to exercise more. And this is a project that we're doing right now. And finally, of course, A/B testing is rampant in websites. How do you test which versions of a website or an app help people? So I'm going to present work especially on learning in education and health. So I'm really excited about the promise of software to enhance education. Anyone can go to a MOOC, Massive Open Online Course, and just start watching videos, whether it's on machine learning. They can attempt problems and get feedback. So you can just learn at the touch of a fingertip. On-campus courses also increasingly involve digital education. If you think about your own company, there's often training that has to happen. How do we kind of use software to ensure that it reaches its potential, where people can learn anything, anytime? I also think about learning more broadly. So if you think about mental and physical health, if you want to tackle issues like depression or people's addiction to smoking, well, how do we do that? One of the most effective methods is actually things like cognitive behavior therapy, which is work from clinical psychology about how we notice and reflect on emotions and thoughts. How do we do the psychological work to change how we respond to situations? It's so effective that in the United Kingdom, doctors can write you a prescription for online cognitive behavior therapy, which can help things like dealing with anxiety or stress, but also help people quit smoking or eat healthier. And so I've done work on this topic in the past, helping people learn CBT or cognitive behavior therapy, and I won't touch on it today. It's just letting you know about it. But here's the problem. When we deploy these online courses, when we give apps for mental health, it's clear that they need to be improved. Sometimes they don't even help people learn at all. Well, why is this? I don't think it's that people haven't done a good job designing it. I think it's a classic HCI problem. Often we can't predict what's going to work in the real world until we actually deploy it, we evaluate it, and then we do iterative design to re-implement it. So how can we actually design technology so we can deploy it because people need it now, but we're constantly improving it while it's out in the field using data from real users? And let me give you an example. So my vision is that we want systems that perpetually improve, just like a real teacher. So let's take a simple, boring example. How do we make a self-improving math problem? So if you think about an online problem in a MOOC, it might give a student an explanation. But your teacher would never explain the same concept over and over and over again in the same way. That's what a MOOC does, right? You get the explanation, so do you, so do you. It just keeps on giving the same thing. What your teacher would have done, and what you guys do when you teach things to people in everyday life, in your company, on your job, is you explain things and it naturally varies. What this means is it allows you to actually detect, well, which explanations do people find helpful on average? And especially, how do we personalize? For example, do people who are new to a topic prefer simple explanations, and those who have enough prior knowledge want more complex ones? So how do we build systems that perpetually improve just like a real teacher does? They keep testing out different ways of explaining or doing things and figure out what's working for different people. So my approach is to think about online experimentation. And I think you all know the side of A/B testing that Google and Facebook and everyone does that you can do on your own website. But I think that we need to do more work bridging this with the tradition in science. Psychology, education, medical trials. It's equivalently just an A/B test, or when I say A/B test, I mean like ABCD, as many conditions as you like. But the kind of methods that people use in scientific research are totally different. They're really rigorous about understanding why something happens. They come up with really good ideas because they've read 30 years of literature, and so their ideas actually seem to work. And so I'm really interested in how we can bridge these traditions. So to think concretely, I'm going to present some work on experimentation in online problems. So for example, we might experiment on motivational messages. Which messages get people to attempt more? Like remember, the more you practice, the smarter you become. We might experiment on questions we ask people. For example, explain why this answer is correct. Or we might experiment on the explanations that we provide people with. And so you can think of what the analogs all are for the kind of tasks that you care about. In this talk, I'm just going to talk about the last one, giving people good explanations. So what's my approach to kind of making experiments, kind of rethinking them so we have self-improving systems? So my idea is that we should reimagine experiments, A/B tests, to be collaborative, dynamic, and personalized. So when I'm thinking about an HCI problem, an education and health problem, First, I'm trying to think of, well, let's design our experiment. What are we going to experiment on? Is it explanations, motivational messages? What are our outcome metrics? How do we measure this outcome? And that's where I draw on work, for example, in cognitive science or psychology. But I think these experiments have to be collaborative. So that's why I work with instructors, with designers of software. So we actually design experiments where we can argue over which conditions are going to be most effective. And then we can actually test them out. It's very democratic. So we deploy these experiments, right? But how do we make experiments lead to improvements on a rapid time scale? And so here's where we use dynamic analysis. For example, instead of assigning people 50-50, what if you analyze data from the first 10 people? And you can then re-estimate, well, what's the probability this condition is best? Well, with 10 people's data, you don't know, but maybe you think it's a 60% chance A is good for getting people to learn and a 40% chance for B. Now get another 50 people. Well, maybe now it's 70% versus 30%. So we have algorithms that can calculate what's the probability a condition is effective, and then actually weight randomization. So if it's effective, you're more likely to get it. So eventually this leads to enhancement. But that's not enough, right? Over time, it should also lead to personalization, where one condition might be better for subgroup people versus others. And so this is where I apply Bayesian statistics and machine learning, where we need actually rigorous ways of saying, while we're running an experiment, let's quantify how uncertain we are about what's effective and for who. And this is a kind of a bit of an open area. There's tons of work in machine learning that could be used here, and Google and Facebook tend to apply certain algorithms, but there's a lot less scientific work about how exactly do you guys pick up these algorithms? When are they appropriate? How do we make them interpretable to designers? So this seems good, right? We can take an A/B experiment, and we can analyze it with machine learning and try and keep leading to enhancement and personalization. But again, this isn't quite hitting the vision of perpetually improving systems, because it's still closed. We've got 2 conditions or 3 or even 10. So what we need is systems that can keep adding new conditions while experiments are running as we get new data. And this is where I draw on methods from HCI, especially crowdsourcing human computation. How do we have scalable ways to keep allowing people to add in new ideas while experiments are running, or to speed up that iteration cycle? So this is now getting a bit more towards self-improving systems. Now, when I first tried to run these experiments, like for example in Khan Academy or edX, when we ran these experiments, we couldn't do all of this. We were happy if we could even run experiments. So what I've done with my research program and others has actually built a back-end web service where if you declare your experiments using this web service, we call it MOOClets because it was invented for MOOCs, but you can apply it anywhere. If you declare your experiments using this, then you can do your simple experiments, but they're API calls and data structures, so you can actually do everything else too. Plug in machine learning, do crowdsourcing. There's a lot of added flexibility. Great, so people get a sense of the overall vision, right? So let me try and give you some examples. So we've got this vision of taking any piece of technology, as boring as an explanation of a math problem, or as exciting as a new tangible interface. And we want to make it perpetually improving by taking the approach of reimagining experiments to be collaborative, dynamic, and personalized. So let me give you one example where we're going to crowdsource explanations from students and then dynamically test out which ones students find helpful. And this system is going to give us explanations that help learning just as much as those of a real instructor. Then I'll kind of think, well, let's be a bit more systematic. So I'm going to present a system from CHI this year which actually lets instructors run experiments. And so I say instructors, but it applies to any designers. It's actually thinking, let's have an approach to experimentation that puts designers at the forefront. How do we make experiments more like a practical tool, not just a scientific one? And then I'm going to give you one simple example of how experiments could be used to discover how to personalize. But I think this is the big frontier. It's a frontier in the sense that for as much as we talk about personalization, when you actually run an experiment to see, does this condition work better, does one interface work better for someone than another, it's surprisingly hard to find evidence for that. So I'm really excited about empirical settings where we can discover those effects. And then the other side of it is which machine learning techniques are going to be efficient in helping us actually discover that. Sort people into subgroups, for example. And this is a setting where we send people emails and we get some evidence that different emails work well for people with different levels of activity. And then I'll touch briefly on the future, and I think this is what a lot of you might be interested in. So we have ongoing work on learning education. We've also got work on mental health, like giving people apps to reflect on why they're stressed. Physical health, like I said, we're running studies where we want to give messages to get people to walk more steps. And The other domains that I've been convinced to work in, so for example, persuasion. A postdoc here who's working with me, William, he convinced me that getting people to donate to charity was a really good setting in which we should explore dynamic A/B testing. And as I mentioned, other applications. I'm really curious to hear what people say. Great, so part one, starting off on crowdsourcing dynamically testing student explanations. Is everyone hearing me okay in the back? Put your hand up if you're not hearing me. Okay. All right. Okay, so this is a paper presented 2 years ago at Learning at Scale. So we call it the AXIS system, Adaptive Explanation Improvement System. What's the problem it's solving? If you look at online courses, often they're just giving people problems and they give answers. And this is really hard for people to learn. There's a lot of evidence from education that if you give people good explanations, for example, that highlight the principle, why an answer is correct, this can be very effective for learning. But when you go to instructors and say, listen, could you write multiple explanations so we can do A/B testing on them? They can't believe you. They say, Joseph, I hardly have time to write one explanation. That's why most MOOCs don't even have explanations all the time. How do you expect me to write multiple explanations? So how could we solve that problem? Well, some other work that I presented Kai 2 years ago, and that there's a long tradition of work on, is I've looked at how prompting people to explain can actually help them learn. So if you've ever had to explain a concept to someone else, just generating it can be helpful for you to learn. And there's a lot of insight into when this works and when it doesn't. But here's what's interesting. What if we actually took your explanation and gave it to someone else? Then your activity isn't just benefiting you, it can actually help the system and other learners. So now we might have a mechanism for continuing generating new conditions, new explanations. Now we don't know if these are any good, so we might actually want to then analyze them dynamically and figure out which explanations other students are going to find helpful. So this is the system learners interact with. First, they see an online problem, and they keep attempting, and eventually they get the answer. They then give an explanation for why the answer is correct. And this is where our A/B test is running. Our metric is asking people, how helpful was the above information for your learning on a scale from 0 to 10? Now, this looks like a simple, obvious choice, but actually a lot of other things that were tried out didn't work. Asking people to rate it thumbs up or thumbs down wasn't effective because it was a binary outcome. And the exact wording in the question matters a lot. Some people will wonder, why are we asking people subjective judgments? We should actually see which explanation helps you learn more, helps you solve more problems. And I agree. But what we found in this setting is that looking at whether people solved the problem more accurately after getting explanation A or B wasn't actually as reliable a predictor of explanation quality as this rating. In part because this rating is a direct function of the explanation, whereas learning is influenced by many other things. But we are going to validate this approach by looking and seeing whether it helps learning later on. So we asked people to rate how helpful it was. So we can run an A/B experiment. We have an outcome metric. We have our conditions. We then tell learners, to help you learn, explain in your own words why the answer is correct. So you guys see why that's kind of sneaky, right? It helps them, or at least they're convinced it helps them, but when they give an explanation that's above 50 characters, and that they check a box saying could be helpful for other people, we actually add it into our experiment. So we keep adding new conditions while the experiment's running. So now the challenge here is, how do we actually make sure we're giving learners explanations that are useful to them? And this is where we use dynamic experimentation. So I'm going to formulate this as a multi-arm banded problem. And this is the most fundamental approach to what's called in reinforcement learning as exploration versus exploitation. So if you're testing out alternatives, that's exploring. If you're exploiting, you're saying, well, I got data from 40 people. Let me exploit that data I have to actually give the 41st person something that's useful. So multi-arm banded is formulated this way. There's a set of actions you want to take. In this case, they're which explanations we give people. Your goal in taking actions is to optimize a reward. In this case, the reward is the rating of explanations. So in a perfect world, you would give people the best rated explanations all the time. But you don't know what's best rated yet. So what that means is that every step from person 1 to person 200, you have a policy. What do I give to person 1 or 2 or 5 based on what data I've seen before about what was rated highly or lowly? we use a policy you can think of as randomized probability matching. It's called Thompson sampling, and it's basically weighted randomization. So if you think about it, there's a probability distribution over explanations. For example, 15, 65, 20% chance of getting explanation 1, 2, or 3. Well, where do these numbers come from? So the algorithm is essentially computing what's the probability that explanation 1 is the highest rated explanation. And if that's 15%, then you present it to 15% of people. Then you might get some more data, and actually there's a 20% chance explanation 1 is highest rated. So now you present it to 20% of people. So you're dynamically updating as you go along. And I should say this kind of algorithm is built into some of Google's websites. And there are many other algorithms you could use, but this is nice because it's very efficient. You can actually implement this in code running even in JavaScript in your browser. And what I think is very good is it's more interpretable than the alternatives, in my opinion, for designers. It's not a black box, we're going to optimize something with some regret guarantees. It's actually every state in time they know what's the probability of someone being assigned to get a condition. So just for the more technical people, and I can go into depth later, basically what's our model of explanation quality? So this Thompson sampling is a Bayesian algorithm, and the key idea is that we started with some prior. Before we see any data, we have some estimate of the probability that an explanation will be rated helpful. So we assume this probability follows a beta distribution with two parameters, alpha and beta. Then we have a binomial likelihood function. And what that means is that we're trying to map, if someone gives a rating to an explanation, for example, an 8 out of 10, we assume that follows a binomial distribution where there are 10 samples, and the probability of each sample being successful is drawn from that beta distribution for the explanation. And so to sum this up, before people see any data, our assumption was that the beta distribution is 19 and 1. And what that means is that every time an explanation is added, our prior is that it's been rated 1, 9 and 1, 10 out of 10. So it's essentially saying before you see any data, act as if it got two ratings, a 9 and a 10. So it's pretty optimistic that it's going to be highly rated, and this helps it actually test it out, but it's not very strong in its beliefs. If it gets a 4 or a 5, it's going to quickly downgrade that. And so every time someone gives a rating, for example, if they give a 7 out of 10, you can think of this as basically 7 thumbs up or 3 thumbs down. 7 thumbs up and 3 thumbs down. So the idea is that basically every time you get an explanation rating, it's giving you some estimate of what's the size of that rating. Is it going to be a 9 out of 10, a 5 out of 10? And so you can keep adding up these estimates of what the true rating of the explanation is. And so in some ways, this is doing things that are analogous to collecting 500 people and doing a t-test. In some ways, it's capturing the same kind of metrics. What's the true rating? Is it high or low? And how certain are we that the true rating is 9 versus 8? And so every time someone gets an explanation rated, we update our estimates of what the true rating is, and then we recompute that probability distribution. For person 59, what's the probability that explanation 1 is highest rated versus explanation 2? Does that roughly make sense? So when we actually deployed this, we did it with 150 crowd workers to test this out. And we chose just 150 because we want methods that can work for a wide range of instructors. 150 is the size of an intro undergrad class. It could be maybe the size of employees in your company who have to take a mandatory training. So it's hard, but could we get methods that work even without having thousands of people? Because then everyone is more likely to use them. So at the beginning, there's no explanations at all. People are just solving problems. As people are asked to explain why answers are correct, they generate explanations, and some of these are long enough, and the user says they might be helpful, so we add them in, and then we get a couple. And so over time, as users are rating the different explanations, 5, 6, 8, 9, we are updating our probability distribution over what's the highest rated explanation. And so at the end, what we end up with is a probability distribution over all the explanations. And so what you can see is it's interesting. It doesn't identify one with high probability. It just doesn't have the data to do that. And I think if we try to achieve that, it won't be an effective system. Instead, it's identifying a few that might all be reasonable, 18%, 13%, 18, 22, and a few that are like very poorly rated. They only have a 1 or 2% chance of being presented. So that's how this system's working. So you can see that this can actually help identify higher or low rated ones. But now you'd ask, well, are these actually effective for learning? And so we did a separate study with a new batch of people. And what we did is we wanted to compare a couple of different conditions to see what's effective. So we had the original problems that had no explanations at all. This is how a lot of things on MOOCs, for example, are. They just don't have explanations with them. And we wanted to compare that to problems that then had explanations from AXIS, from the Adaptive Explanation Improvement System. Which of these is better? Are these AXIS explanations any good in helping learning? We also had a condition that had filtered explanations. And I mean explanations that are filtered out. This is explanations that the system says have less than 5% chance of being the best. And finally, as a gold standard, we compared to an explanation the instructor actually wrote themselves. So we could see, how close does the system get to meeting a real instructor? So what you see on the vertical axis is accuracy increase. So we have a pretest, people come in and solve a bunch of problems, and then in the original problems condition, they just get the problems, no explanations. Then they actually get a post-test. So we actually evaluate how they actually learned how to solve problems better. Are they doing better on those problems as a result of having been in the original problems condition or the problems with AXIS explanations? So this accuracy increases pre to post. And we also included transfer items as well. Not just the exact problems on the pretest, but other problems that tested a related concept. So what's the key insight here? So even though these AXIS explanations are crowdsourced from users themselves, once we run them through this dynamic experimentation algorithm, we do get explanations that actually measurably help learning. Now, some of you will be skeptical, right? You're going to say, well, of course the explanations helped. Any explanation would have helped learning, right? So these are the filtered explanations. They were generated by students, but the algorithm actually gave them less than 5% probability of being the highest rated. So they're explanations. But what's interesting is that they actually like getting no explanation at all. They don't help learning. So that's for the skeptics in you. I was a skeptic too, that's why I included all these conditions. One thing about A/B testing is, the first lesson is, most things have no effect whatsoever. A/B testing keeps you honest. Things that you swear are so obvious that it would be unethical to even run the comparison, no effect. So I was impressed by these results. So the final question is, how good are these compared to a real instructor? And how good would they have to be for like Daniel or Ali to trust me? Would it have to be 50% as good as the explanations, or 20%? Actually, there isn't a significant difference between the instructor's explanation and those that were crowdsourced and dynamically tested. They don't significantly increase learning in this situation. The instructor said that they did prefer theirs, they had to be honest, but they couldn't actually see large differences, and they would actually like to see more data about what's effective. So what are the contributions of this work? So the first is actually this idea of learner sourcing, right? Crowdsourcing from learners, and they are actually self-interested contributors. They're not being paid. They're being paid in terms of benefiting their own learning. And the second is, here's an example of running a real-time dynamic experiment to put data into practice. Now, I think this is just the first step, right? There's several limitations and many future directions in this work. There's a whole research agenda and like a couple of PhD theses. One key direction, I think, is to expand it beyond just explanations. For example, if we look at something like someone watching a video, if we ask them a pop-up quiz in the middle of the video, what's the key assumption of naive Bayes? Well, they can write an answer, but then we can actually recycle that question-answer pair on something like a discussion forum, like Stack Overflow, where you can now see, here's how we crowdsource or learner source answers to questions, which could then be put into a discussion forum. And then we might actually think about using A/B testing or randomized experiments to test out which ones people find helpful, help them learn. Another one is teacher input. So how do we, if we're really big into this idea of human computation, where in this study we actually showed, here's how an algorithm works with students. We've structured the system so that students are generating explanations, they're giving ratings, and the algorithm's helping to sort them. How do we bring teachers into the loop? For example, I think there's such situations where student explanations might be better than teacher, and where they'll be worse. For example, suppose students have a robust misconception. That's actually a case where they're going to think an explanation is fantastic, because it's reinforcing an incorrect belief they have. That's where you need a teacher to be able to step in and actually flag things, or redirect the algorithm, or change the way what the algorithm is trying to optimize. And so that kind of leads to the second line of work on instructor-centered experimentation. So the idea behind instructor-centered experimentation, which we presented at CHI this year, is that we want to give instructors an end-user tool to run experiments in their class. And so I'm providing the output of this, but I think what motivated this is the idea that experimentation tends to be a scientific tool. How do we reconceptualize it so it's actually a practical tool for instructors to use? And so our goal here was to reduce the time and the programming effort instructors needed to run experiments, where they could actually deploy it directly into their course. And so this app here, which works with Canvas or Crocus, which is U of T's new system, it also plugs in via LTI to any learning management system, probably whichever one your company uses, and it also works as a standalone app. But the key idea is that the instructors could actually create a quiz, and then they were able to author alternative messages that show up. Feedback messages, so someone sees a quiz question, just like the previous study, they see a problem, they get the answer, and then they get a feedback message below, or an explanation, or a hint. So the instructors actually were able to author what these look like, just by going in and typing these different alternatives. For example, this person just had a feedback message, correct. Since F is always negative, it's always decreasing, and the F reaches its lowest point at the far right endpoint. But then this instructor actually came with something new. They said, the problem is that students are just not reviewing the video. I think they need some kind of prompt to realize the point of a question is to help you review a concept. So they had the exact same feedback message as condition A, but in condition B, they added on a tip, which is, if you'd like to review this sort of question further, look at your notes about how we found where the function G was greatest and least, or take a look at this video. So the idea is now the instructors design their own experiment, and they can actually collect data about what students rate as being helpful. Another key part of this, of course, is also the dynamic experimentation. So instructors seem to be enthusiastic about the idea that the experiment wasn't just giving some results that might be published. It was actually using data from student 5 to help student 6. So we're again using Thompson's sampling to choose the best conditions. So here's an example of an instructor dashboard. This is a different instructor, so they wrote a quantitative explanation for how people should do computations with statistical power of a hypothesis test, and they wrote an analogical explanation, which is more saying, statistical power is kind of like a telescope. The bigger the object you're trying to find, the less power that you need. And so they were worried the analogical explanation would not be well received because it wasn't as technical. They didn't have graphs and numbers in it. But what you can see here is, at least in this sample, there's a tendency where students might rate the analogical one as 7.48 versus 7.26. So there's a trend in that direction. And more students end up in that condition because while the experiment's running, we're putting more people there. And so by this point, there's a 77% chance that's really high rated explanation. But because we're not sure, the experiment's continuing to run. We're still collecting data. So we deployed this overall with 3 Harvard instructors. And the general comments were that this kind of tool lowered barriers. I'm not aware of any tools that do this kind of thing. They felt that actually just thinking about experiments helped them reflect on pedagogy. I never really seriously considered testing multiple versions as we're now doing. So even if we don't get any significant data, that would have been a benefit in my mind. And so you might start to think, well, what's the value of just almost like thought randomized experiments or thought A/B experiments? Just having people think, well, how do you measure the outcome? What alternatives would you come up with? They liked that it made research practical. So it's put in the hands of the teacher to understand how their students learn, not just in broad terms, but specifically in their course. So when they thought about the collaboration with me as a researcher, they said, you must know plenty of general things about how students learn, whereas I know specific things about how they get calculus. So this is the collaborative experimentation idea, where we each bring in different ideas that we can then integrate and test out. But I find these collaborations are a lot quicker and more precise than how I've collaborated with people in the past, because we're talking about an experiment. All our discussions can always be traced back to, let's compare A, B, and C, let's change this thing. Let's argue over the best way to measure learning. And finally, they really appreciated that the multi-arm banded algorithm dynamic experiment helps students directly. This improved the experience of many of the students by giving them answers that are more helpful. The earlier ones can help improve the experience of the later students. That's pretty neat. So what are the student perspectives on this? Well, when we asked for ratings after the third experiment, students actually seemed to be positive towards the approach. For example, one said, I assume companies are always A/B testing on me. At least the data I provide can help other people learn. So maybe they're a bit cynical, but I do agree with them that we're getting data that could actually help them or other people learn. So the kind of key takeaway here is, I think this is just the very beginning, because now we're really excited about running more experiments with instructors. For example, this rating of subjective helpfulness, that's reasonable because when instructors teach, that's often all they have, whether students actually seem to find an explanation helpful or not, or if they find the feedback message is useful. But the instructors actually, once we got them a bit hooked on doing experiments, they were then spontaneously interested in coming up with learning measures. So they want to then actually go deeper. So this is a nice entry point. And I think there are a wide range of questions we can ask with this. I think this is another 10 years of research on collaborating with instructors to run these kinds of experiments, like in online problems, but also other settings. So one thing we're looking at now is basically, how do we come up with motivational interventions, like sending people messages that will kind of get them to think of intelligence as being malleable, so they work harder, or sending people activities that help them plan their week so they can set goals. How do we test out which of these is effective? So I just want to, the last part of the talk before I turn to the future directions is just give you one example of how experiments could be used to discover how to personalize. And I think this is just an illustration. I'm really working hard to figure out how we can run better experiments in this. So we're sending people emails in a MOOC. And we're trying, the instructor said, I would like to get people to respond to me about why they haven't been engaged in the course. How do we increase the response rates? So I want to send out surveys. So we actually ran a really complex experiment, but let me show you two conditions from it. You got an email asking about course participation, and there was a brief version. Could you just take this short survey? Then there was one that mentioned the fact they've been absent. So it only differs by saying, it's been a while since you logged into the course, so we're eager to learn about your experience. And now we're going to look at response rates. So what do we see overall? Well, the response rate is actually not different between these two conditions. So does that mean we just give up and go home? Actually, when you break it up by low and high activity, low activity is people who are active for 0 or 1 days, and high activity is people who are active for 2 or more days. But they recently stopped coming to the course. So the brief message is actually leading to slightly higher response rates. There's a trend for low activity students, maybe because they're more likely to read a brief message. The high activity students are more likely to respond to the message that mentions that they've been absent, maybe because they want to justify why they were more engaged early on, but now they've dropped off. So what's interesting here is, well, if you actually think about, well, how do we optimize response rates? You could have thought, well, it doesn't matter, just give brief or mention absence, there's no difference. But if you actually give people a low activity brief message and people high activity mention absence, then you can actually increase how many people are responding by about 14%. And so I think of this as optimizing through personalizing. We've designed the same number of conditions, but because we're using machine learning or statistics effectively, we can actually figure out how to deliver those to different people. And this is just a wide open area in terms of which methods are best and how to do this. So the main method that people apply and that we're applying now is contextual bandits, which have been used widely in things like advertising, but it's less clear when you apply them to randomized experiments. How do you do things like figure out how many experiments you run at once? How do you bin groups of people? And especially, how do you do this efficiently? So from a machine learning perspective, the exploitation problem just explodes once you've got personalization. Because in a way, you're never sure whether you should stop experimenting and give everyone A. Because there might be some subgroup who you're neglecting. It might be that, for example, one group is underrepresented in the population, for example, women. And so the average effects you see are driven by something that's impairing a subgroup. So just to give an example of the kind of things we're pushing now, it's really trying to think about high-dimensional experiments, what are called factorial experiments in some disciplines, and what you would think of as running as many experiments as we can at once you can design them to be a bit independent. So you could actually imagine that you run a 3 by 3 by 3. So 3 experiments, 3 conditions. We've got 3 different subject lines: return to course versus fill out a survey versus how are you doing. We've got 3 different intro messages and 3 different bodies. And there's a lot of context, right? People's age, how many days they're active, what country they're from. And so in these kinds of settings, I'm really excited about trying to figure out which conditions work for different people, and also handling the statistical methods you need to analyze this kind of data. The short story is, we're pretty sure, and statisticians are pretty sure they're good ways to do it. In fact, statisticians are the people who are least worried about this. It's more often like behavioral scientists or instructors or computer scientists who worry. But I think these things need to be shown to people. We need to have real-life demonstrations of applying it. Just to give you one illustration of how this could look, right? So essentially what these algorithms might be trying to do is say, well, when you do randomization, and you start off with, let's say, 33% across the board for different age groups, you might actually send data to 500 people, and then you actually change the probability of assignment. So maybe now, for example, for 18 to 22-year-olds, there's a 40% chance of them receiving subject line A. Well, where does that number come from? The idea here is that you're actually looking at response rates. For example, 3.8% of people respond to A versus 1.6 to B and 2.3 to C. So this is a really simple example. It's really just illustrative of what the algorithm might be doing. But the idea here is that you're kind of updating your prior to your posterior. You're saying, well, you're probabilistically personalizing. For a different subgroup, what's the probability that this condition is best? Let's give it to them with that probability. And that probability may vary for different subgroups of people. Just to give you an illustration of one simple way, some simple heuristic you could use, and the key challenge is figuring out which of these heuristics are effective. Great, so just to give you an overview, I started on this vision of perpetually improving systems. How do we take a user interface, an app, and just make it constantly improve the way a real human being would? And my approach is to say, well, let's reimagine experimentation to be collaborative, dynamic, and personalized. I give one example in education where we crowdsource explanations by asking students to explain their reasoning. And then we dynamically test these out using multi-arm bandits to figure out which explanations are higher rated. And this gives us explanations that help learning just as much as a real instructor. I then thought about how we can actually make experimentation a tool that's helpful to instructors and designers. So we built a system that actually instructors found lowered the barriers for them to actually design experiments. It helped them reflect on pedagogy, and it gave them a clear pathway where they could see how the experiments they run would be practical. It actually helped students. And finally, I give you one illustrative example of what I'm really excited about doing next. Using experiments to discover how to personalize different groups of people. How do we design experiments with these kind of hypotheses in mind? And how do we have multiple experiments running at once? So maybe I'll just close on a few future directions, what we're doing right now. So there's continual work on learning. So both of those studies I presented, I see those more as a first step in a wide paradigm of research. There's 10 years left in each of those in terms of deep work we could do. So crowdsourcing explanations, personalizing them, and especially using contextual bandits. These are bandits, algorithms that basically think about what conditions best for a subgroup of people where we have context. We have a set of event that describes features of the person. Another area that I worked on in the past I'm turning back to now is mental health. And this doesn't have to just be for a clinical population. Every one of us could benefit from apps that help us reflect on stress. Another project is basically thinking about physical health. So let me talk a bit more about those. So in the context of mental health, this is an activity we call 10 questions. This is for the grad student at University of Washington. So we ask 10 questions that people can ask themselves when they're in a stressful situation that help them reflect on why they're feeling that way and how they could think in alternative ways. So we want to A/B test which questions are best and personalize them based on someone's state or even their inclination to answer questions. So for example, what alternative ways to think about your negative emotion? Is that a good question to ask someone when they're stressed, or is it something else we should do? Should we just show them a YouTube video of a cat? You can come up with the ideas you think are best. In the context of physical health, what we're doing right now is we've worked with a Singaporean company to actually embed this MOOC-led web service for A/B testing into their app. So we want to get people to exercise more by crowdsourcing messages from them. So we send them a message like, what's your plan for exercising today? And they can check a button saying, I want to suggest a different message. So they can say, I don't want to hear that. I need to hear something like, you're being lazy, get out of the house now. So they can personalize because they're telling us what message they want to receive. But you guys can see how that's helping everyone else, right? You can take their message and try and give it to similar users. You can A/B test if it's effective. And so I think the broad theme here is that I think a lot of the problems we think about for mental and physical health, we think of them as being biological in nature, and they certainly are, but there's a lot of research on that. I'm really interested in how we can think about the science of behavior change, which National Institutes of Health in the US has called for. And I'd love to find out more about CIHR in Canada. I've just recently arrived. But the kind of key idea here is that some of the solutions to these biological problems are actually psychological and computational. How do we build technology that can discover how to get people to change their behavior? So another direction, which Wei Wen Liang has convinced me is really important, is looking at persuasion, like how do we encourage people to give charitable donations? And then we can A/B test what kind of messages we ask people, what kind of information we give them, what questions we ask them to help them reflect. Maybe all of you have other applications. So you have ideas for industry projects where there's a good metric of behavior. They're going to allow us to run experiments, and they're going to pass us data in real time. So anything like that, I'm always, at least in principle, open to collaborating on. And that would be using things like this open source MOOClet web service, which we're developing so people can plug in A/B testing that involves crowdsourcing and machine learning. Yeah, and like I said, if you're interested in just getting news or updates, feel free to send an email to iiinterest@googlegroups.com to say, you just want an update every month, you'd like to attend some of our weekly meetings, you'd like to hear about the talk series or present, or just see course materials we put together for learning about these methods. All right, so just to close on the overview, I think you can see now how what I presented kind of fits into those future directions. All right, so thank you for your, thank you.
Great, thanks a lot for the talk.